Just before in the earlier session today, we were talking about finite difference methods. And this is where we were. We were sort of discussing how a finite difference method is constructed. Essentially, we've got a number of points where we use information to approximate the derivative. What we're going to do is we're going to talk about choosing some point xn. I did a sneaky change in notation. This used to be an I, but I used n in the notes, so I'm going to keep using n here. We choose a neighborhood, for example, n minus 1, n, and n plus 1, these 3 points shown here. And that leads us to the centered finite difference method that happens to be second order. Now, second order has pretty much the same meaning as what we found it did for time stepping methods. It means the error looks like a squared spatial step. It's a little bit different in the sense that we talk more about local errors now than global, if you want to relate it to time stepping. But what we're going to do is we're going to approximate the derivative by these function values. The idea being is that you sort of pretend that you know the function values. What we'll actually see is that when we proceed through this method, we'll get an equation, a linear or set of linear equations for our function values that we can then solve, because it's just a matrix problem. So this is what we've got. We've got k as our bandwidth, if you like that's the number of points that we're taking. So in this example, it'll be minus k be 1, right? So minus 1 to 1. And then we're going to rip out the Taylor series. So I assume you all remember the Taylor series from first year. You're all happy with Taylor series, yes? Yeah, got one happy button. I'll write down the definition anyway. This is obviously for a sufficiently nice function, but just about every function you'll come across like that is sufficiently nice. So this is the Taylor series of big F at x naught. What we're going to do is we're going to approximate or we're going to use this kind of Taylor series to approximate f, little f, at xn. So little f at xn is, approximately. This is exact if you do if you do all the terms, if you do the infinitely many terms. But we're not doing infinitely many terms because that's not possible. We're only going to do a few. And then we've got what we call higher ordered terms, right? So that's like the leftovers. At x equals xn plus 1, right? So we're now looking, we've done our Taylor series around the point xn, right? And we're going to look at xn plus 1 with our Taylor series. We're going to use the Taylor series to approximate our function value there, and also xn minus 1. So we just slap this in. Right, that one doesn't change because it's already an xn. That's an xn, right, doesn't change. This, however, becomes xn plus 1 minus xn. Now we can immediately work out what that is. That's delta x. That's our spatial step, right? And of course, oops, I forgot there's a little square term there, plus this extra bit here. And I'm just going to write delta x squared here, because that's the difference between xn plus 1 and xn. So it's pretty clear that at minus 1, all I got to do is go through and change the letters around a bit. So I'm just going to copy and paste these things. So firstly, oops, sorry. So firstly, let's just write delta x in here explicitly. And then let's do the negative. So xn minus 1 minus xn, well, that's not actually delta x anymore. That's minus delta x, right? Here you're going to get a minus, you're going to get an xn minus 1 minus xn. That's going to be minus delta x, but we've got a squared, so that turns out to be the same as delta x squared. Anyway, so the only real difference we have is we've got the same expressions, just with changed sign. Right, so all I've done so far is I've used a Taylor series to approximate what happens with my function at 3 neighboring points. So I now have information at the middle point and the 2 sides, right? So I've got information about the function there. I've got to now put this together and try and identify stuff about the second derivative. So what we said in our part at the start of this is that we were going to write, oops, wrong color, the f squared dx squared at n is equal to, or approximately equal to, the sum aj fj, right, for j equals n minus k, n plus k. So let k equal 1. We've got approximately a minus 1, or a n minus 1, times f of n minus 1, which we just determined up here. Then we've got the midpoint, which is plus a n. That's just f of x in, because there's no reason to expand that in a Taylor series, because we sort of pretend that we know this value. And we've got the other one. And this is just copying down the Taylor series result from before. Note that I've neglected the higher order terms. I've just ignored them. Right? Obviously, that's going to contribute to my error. Right? the higher order terms feature, in this case, terms like delta x cubed, for example. So we know that the first thing that we're discarding is a cubic term, if you like. So because we've discarded a cubic term, we say that the approximation itself is accurate to second order, because the third order one is the first terms where we start to see inaccuracies. We make this exact for these terms. Right? The approximation comes when we chuck away all of the higher order terms. So what we have to do is we want to approximate this by this, and we need to find these, the a, n minus 1, a n, and n plus 1. So by writing this f dashed xn to continue with the notation that we've used, we're going to equate these terms across the equal sign. We're going to equate like terms, right? So note that on the left-hand side, we do not have an fx term. So the sum of the fx terms on the right-hand side has to equal 0, right? Because we're assuming this is a general function, and there's not necessarily a relationship between the derivative and the function itself. So this sort of thing, we've got to find an equation for the f's, the f primes, and then we've got another equation for the f double dashes. So 0 equals a n minus 1. So that's this term. Oops, hang on, what am I? I feel like I've blundered slightly. Oh, I have blundered slightly. I made a mistake copying these down. They should be xn's, not x plus 1's. They come from here, right? I should have just copied an xn in there. All right. So yeah, so an plus an plus 1 f of xn, like that. Right, that's our first equation. Because there's no f term on the left-hand side. There's no f dash term on the left-hand side either. We're also left with, except that has a minus sign. That one has a plus sign. So let's just sort all this out. These derivations tend to be very tedious. There is an f double dash term on the left-hand side, and there's the 2 on the right-hand side as well. So we need to sort them out. We need to make them equal. That turns out to be remember, because we have the squared term, both the signs are positive. Right, so this is now a set of equations that we're working with. These are 3 simultaneous equations for the a's. Right. Now, we can obviously just knock out the f's, the f prime and the f double prime, to obtain the following system. an minus 1 plus an plus an plus 1 equals 0. an plus 1 minus an minus 1 equals 0. So you see that these two are obviously equal. And you also see that an plus an minus 1 equals 1 from this equation here. Oops, equals 2, because I've got to multiply by the half. Right, so we're just solving the simultaneous equation now. It implies an plus 1 equals an minus 1. Here, we see that an, right, if we sub in an plus 1 plus an minus 1, right, that's going to be 2. So an is equal to minus 2. And obviously, if we substitute this one in there, we're going to get an minus 1 equal 1. Right, when we use our right, that's just by doing substitution. So that's all pretty clear, I hope. Oh, oops, I forgot a value of delta x. Right, so here I've got delta x squared actually, and I forgot to include that in this equation here, delta x squared. So this equation becomes delta x squared. So this an becomes 1 on delta x squared. Delta x squared. That just propagates all through the coefficients like that. Okay, and for some reason, I seem to have I've got a different answer in my notes, which I now wish to track down as to why, what mistake I've made here. This is correct. That's in agreement with my notes. This is correct and in agreement with my notes. This is correct and in agreement with my notes. It is straightforward to deduce that an minus 1 let me just check this on just make sure I've got this. This looks right and it fits with my memory of the coefficient values. Yep, this is right, I believe. Yes, good. So this is correct, and what we find is that our approximation, right, because remember this is what we're actually trying to approximate at x equals n. That's approximately equal to this coefficient, 1 on delta x squared, minus this times f at xn minus 1, minus 2 delta x squared, like so, and the other one, our final coefficient, like this. So that tells us how we combine these 3 points, right? Doesn't tell us what f is, it just tells us how we add them up. So this is n minus 1, this is n, and this is n plus 1. All right, so this is what we call the centered order finite difference approximation. Remember that there are terms that have order delta x cubed, right? So that, if you like, is the error associated with this method. Okay, so let's just pause there for questions. Is everyone happy with this? Did you sort of understand how to go through by starting with a Taylor series and then figuring out the coefficients of the series that we constructed by equating the terms across the equation? Is everyone happy with that? No happy faces, no faces at all. All right, we have one happy face. We have a sad or a confusey face. All right, because of the confusey face, I'll do another version of this, right? I'll finish this example, and then I'll take a crack at a different type of finite difference method, because there are actually multiple versions of this. What we have is an approximation to our derivative that we want to put into our equation. So we started with an ODE, but it could be a PDE. It really doesn't matter. Oops, this is an X. Hope I didn't write that up here. Nope, I wrote X. That was a one-off. So our ODE was this, right? And what we've done is we've reduced it to 1 over delta X squared plus oops. Right, that's our new approximate equation. This is what we call a difference equation or a recurrence relation. It's kind of like an arithmetic progression. It's kind of like the time stepping methods we've seen, except it's just a bit more complicated. We've got an n minus 1, an n, and an n plus 1, and we know none of these things. However, we know that n starts at 1, for example, and goes up to big N minus 1. Right? We actually have boundary conditions at the far end. So this is how we traditionally label our points, right? So this will be our boundary condition there. If we label 0, 1, 2, 3, blah, 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 n minus 1, that's like the points that we're interested in. Right, that's our discretized interval. What we can do now is, because we've got those equations, we can write them out. Right? There's n of them, but we can make a start. If n is 1, then we've got 1 on delta x squared f x naught, right? Plus or minus, I'll write plus 1 minus 2 on delta x squared fx1. Right, that's combining those two terms. Plus 1 on delta x x2 equals 0. Right. We can write out this for n equals 1, n equals 2, blah, 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 right? Or we can write this as a matrix vector product. So let's start writing a matrix. Let's leave the first row empty for now, right? We'll leave that base for the first row. This is the second row of our matrix, 1 on delta x squared Second column is 1 minus 2 on delta x squared. Third column is 1 on delta x squared. And then everything else is 0, all right? We multiply this, oops. The vector that we're multiplying is f x0, f x1, f x2, dot f xn, dot f x big N, right? That's our end point. All right, so here we have boundary condition, right? We know that f of x, x1 has to be equal to something. So we just fix it. It's equal to a. Everything else we know, it's equal to 0. That row is equal to 0, that row is equal to 0, dot, 0. Right down the bottom, we've got this other boundary condition. It's equal to n, f of xn equals b, right? There are boundary conditions. Right, so we've got this vector of zeros and 2 non-zero entries, which are our boundary conditions. We want to force, right? This is entirely just a statement of a boundary condition equation. Right, so x sub capital N is equal to L. Right, that's a statement of our boundary condition. Everything else in the equation, all the other terms don't feature. 0. If we write out the second equation, we won't see an x0, we'll only see an x1. 0, 1 minus delta x squared, 1 minus 2. Right, and I know this pattern is going to keep going, right? I'm going to get a matrix which has entries that are just 3 diagonal bands, right? Except for 1 there and 1 in the corner there. This band is going to be one of the delta x squared. This band is also going to be 1 over delta x squared. And this band for this particular equation is going to be 1 minus 2 on delta x squared. All right, so that's how we construct our finite difference problem. And what we've done is we've now gone to we've gone from an ODE to a matrix problem. Now, this matrix problem is completely specified. All we have to do is invert this matrix, or we use back substitution, whatever our favorite matrix solving technique is, and we're done. We extract F. Right, that's all. Right, if you wish, we can write this as MV equals X implies V, or sorry, that should be an F. F vector equals M inverse X, right? That's it. That's all we've got to do to solve this problem. Matrix conversion is hard numerically, especially if you've got a big matrix. So we actually tend to prefer using back substitution techniques. There's a really fast back substitution technique for what we call a tridiagonal matrix, which is these 3 bands here. So that's called the Thomas algorithm. It's well known. It's inbuilt in everything like MATLAB as well. So that's what we'd use to solve it. So in summary, we extract finite difference coefficients to approximate derivatives. So these coefficients, these are our a n minus 1, a n plus 1, for example, to approximate the derivatives. Now, once we've done that, we form a matrix problem. We invert the matrix, or solve with back substitution. And because this is hundreds of points, this is a numerical computational solve. Of course, you can also use these finite difference schemes to form an approximation of the derivative. If you have some function f, right, you can put f in a vector. So you've got some matrix like this. You multiply your vector, your function that you want to differentiate. You multiply it by this matrix, and then you get df dx, for example. Or, you know, if that's like a first derivative approximation, you could have a second derivative approximation, and so, etc. All right. So are there any questions about that with what we're up to? I'll come back and take another crack at explaining finite differences, just sort of skimming over it again with a different example. What we've used, or what we've done, is we found a method that works really well at internal points, right? We need a bandwidth of 3, so we can always find the derivative at this point, any of the others, because it's got a neighbor each side. This point and this point does not have a neighbor each side. So if you don't have boundary conditions, or you've got Dirichlet Neumann boundary conditions or something, you can find that you don't have enough information. You might need the derivative at those points, and you've got nothing, right? In these cases, we use what's called a non-centered method. So we could use, to evaluate the derivative at this point, we could use information from here and here. Still the same number of points to form the approximation as we used for the centered method, but it's now not centered, it's offset, right? This one's called the forward method because you're using points ahead, and by analogy, this is called the backwards. So we'll derive a forward approximation. And let me just check. I'll just do the let's think of a nice simple one. Yeah, I'll do the first order, first derivative, right? Because effectively, it's almost the same as Euler's result anyway. So I want to approximate first derivative. Now, order means here we use order to talk of the derivative, not the accuracy of the scheme, right? So we have to know a little bit more information. It turns out that the first order forward finite difference with 2 points is first order accurate. Whereas the centered method with 3 points is second order accurate, right? So the more points you have, the more accuracy you have. If you're only using 2 points, the best you can hope for is kind of first order accurate. That means we're going to approximate this operator here, this derivative, by a, we'll just label this point x0, and we'll label this point x1. So a naught f naught, so f of x naught. This is at naught, plus a1 f of x1, right? That's the approximation we wish to use. And we're going to use a Taylor series again, right? We're going to use the Taylor series at f of x naught. We're going to pretend that we know everything about x naught. And we're going to expand this one, right? So the Taylor series of f of x naught, or f of x at x naught, that's what I really want to say, is f of x equals f of x naught plus delta x first derivative x naught x minus x naught plus higher order terms involving involving delta x squared. All right, so I'm not going to write out what those terms are. I'm just going to say that they're there, and that's the kind of thing that we're going to neglect in our finite difference approximation. So we want to replace this f of x1 with this Taylor series. X1 is just equal to x naught plus delta x, so that's what we're going to replace this with. So we have f prime of x naught, that's this written in different notation, equals a naught f of x naught. Now we're pretending that we know f of x naught, but we don't know a naught, and we don't know a1. So here I've substituted my Taylor series. X1, right, is x naught plus delta x minus x naught. So that's going to be delta. Oh, oops, that delta doesn't exist. That's a Sorry, I made a mistake. I jumped ahead of myself. And there's no 2 factorial either. That's the delta. Yes. Sorry about that. I jumped ahead because I knew that was going to be delta x. So that one goes there. All right. So now we equate like terms. Right. So I'm just going to group up the like terms. This is something that catches a lot of people. And I'll write out like terms on both sides of the equation. 0 f of x naught plus 1 f of f prime x naught equals a naught plus a1 f of x naught. Right, there was no f of x naught term here. I introduced it explicitly and multiplied it by 0, right? So these are mathematically the same thing. This term, 1 delta x, like, whoa. Hello? Am I still good? Could someone just ping the chat? Make sure I'm still being heard?
Yeah, it's about you, Duncan.
Yeah, okay, cool. Sorry, I just got some really weird like noise and feedback. I thought that my connection had dropped out again. All right, so let's highlight this one in yellow, right? And we're equating it with this one, right? Because we can't get an f prime from an f or vice versa, right? So the only way that this equation is true is if this coefficient happens to be equal to the coefficient on the left. So that implies a0 plus a1 equals 0, right? That's what this equation tells us. The other equation, this term here, right, the f prime terms must be individually equal as well. So that tells us that a1 times delta x equals 1. So this is a very simple simultaneous system to solve. A1 equals 1 on delta x. This one is a0 equals minus 1 on delta x by back substitution, right? We know a1, so now we can find a0. I'll just draw a little arrow so you can see the order in which these are calculated. So our approximation, our finite difference, it's first order derivative. It's forward and it's 2 points. Equals 1 on delta x times f of x naught. Oh, that should be naught, not an n. Plus 1 on delta x f of x1. Right, and again, that's a first order method because we neglect, it's first order accurate because we neglected things that looked like delta x squared in our Taylor series approximation. So hopefully that outlines how all of these schemes are generated. Now, I personally find working out these schemes to be quite entertaining. However, sorry, hang on a sec. I want to share. Uh-oh. I want to share my I'll share my screen. Right, so you should all see my Chrome, just a Chrome tab now. All of these finite difference approximations, they're very well known, and they've been well known for a long time, and they're tabulated in plenty of different references, right? If we weren't looking at Wikipedia, we'd be looking at a thick, dusty old book called Amerowitz and Stegen. These are the central finite difference methods. They tell you the points. So this is 1 point to the left, 1 point to the right, second order accuracy, first derivative. These are the coefficients, right? Implicitly, there's a delta to the order of the derivative, right? So they've used h for their spacing in this case. So that just tells you how to, this is a table which tells you the sixth order derivative to sixth order accuracy, right? They're the coefficients. They're the numbers that you have to plug into your, for your A0, A minus 1, A1, etc., to get that level of accuracy for that derivative, right? So you don't actually have to think, these are the forward ones, the corresponding ones. You don't actually usually have to derive any of these approximations in practice, right? So they're all tabulated and exist quite happily. Okay, so do we have any questions at this point? So we're all relatively happy. I think we can take a break for 5-10 minutes, resume at 17:10, and we'll actually try to work through one of these. We'll try and apply a finite difference approximation to an actual equation so we can see how this works in practice. All right? So I'll start talking again in about 10 minutes' time. Hello? All right, let's resume. Let's look at the next computational or numerical exercises, which discusses using finite difference approximations to solve the one-dimensional heat equation. So if I share my screen, sorry. So this is the last one we did was the Adams-Bashforth one. This is now how to solve the 1D heat equation with a finite difference method. I might probably not go through all of this example. What I'll probably actually do, I think it's actually at this point in our numerical education, a really good idea if I step through how to get this pseudocode. And how to derive the numerical method that we're about to use. So, yeah, I don't think I'll be able to finish that in the 50-minute slot, but we can resume, or you can attempt that yourselves, or we can leave it for the notional tutorial on Fridays. And so on. Like, I'll get us part of the way through this exercise, I think. I think it's probably also a good idea that you sort of attempt a bit of the programming on your own as well. We're going to have to approximate the time derivative. I'm going to have to approximate a second order spatial derivative. We've got 0 boundary conditions, so B1 and B2 are actually 0. Because it says symmetric 0 boundary conditions. All right, so I'm going to switch back to OneNote so we can talk about firstly the numerical approximation that we've got to figure out, and the pseudocode. So using FD methods for du dt equals k d squared u dx squared. I think for whatever reason I decided to do it like this. So I've discretized an interval in a different way, but it doesn't actually change anything where we start and where we finish. All right, that's our computational problem. I wonder if B1 and B2 are supposed to be 0. Oh well. It's easy enough to change as we go along. Our first task is to discretize our equation. Discretize means apply one of these finite difference methods, or two of these finite difference methods, to approximate those derivatives. So we replace and du dx squared with finite difference approximations. Now, because they're PDEs, this is a PDE and these are partial derivatives, this working out is going to become messier. We're going to have a time subscript and we're going to have a spatial subscript, right? If you like, we're going to work on a net, it's called a net sometimes, that looks like this is our spatial part. Right, so that's 3 points. So this is n minus 1, n plus 1 in space. And we're going to have a forward finite difference. So first order derivative and first order accurate. This is going to be our time. So this is going to be I minus 1, and this is going to be I. Okay, so this might look a bit strange, but this shows you what spatial and temporal information we're using to advance our solutions. So our individual derivatives are approximated as follows. Right, we worked this out in the previous hour. We know that this is minus 1 delta t now, because it's a dt. U at xn, comma, t minus ti minus 1 plus 1 on delta t u xn tn. Oh, ti, sorry. The subscripts have got to be different. So that's our temporal derivative using a first order forward 2-point approximation. Now for the other derivative, we've got to do a second order approximation, or approximate a second order derivative. And we worked this one out around 3 o'clock or earlier today. We worked this out as 1 on delta t squared. You can, of course, always just go to Wikipedia and look these up. N minus 1, 2 on delta. This is a spatial approximation, so it'll have dx's instead, or delta x's instead of delta t's. Like so. Okay, so with these 2 bits of information, we just take these and plug it straight into our PDE, right? So goes over here. This bit goes on the right-hand side. It's not a difficult concept. It's not even a difficult rearrangement. It's merely tedious. And we have to be very careful copying all the bits and pieces. We'll just maintain the equal sign. I mean, these are approximations, but we'll just maintain the equals. We've got a k there as well now, so we've got to take care of that. Okay. So this awful long expression is what we wanted. Now we've got to try and kind of collect this into something that we really can work with, something that we know about. So I'm just going to pull up. I'm just going to check my notes to make sure I haven't blundered. Nope. So far, so good. I don't believe that I have blundered. Okay, the question is what we're actually solving for, right? That's a bit obscure at the moment. We want this. We want to know U, the temperature at that new discretization point. We're going to loop over the N, so that's going to cover all our discretization points, and Ti is our new time step that we're projecting forward to. Okay? So we're just rearranging this awful expression for this little bit. First thing that we can do is we can multiply through by dt, clear some stuff. We'll get we've got a common factor of dx squared and the k as well. So we'll try and deal with that. When we do that, when we multiply through by dt and take care of the common factors on the right-hand side, k delta t. Then I've got to write this in order. Right, we know that this is still what this is sort of what we're solving for as well. Oops, I got rid of that term already. Minus 2 plus u. Okay, we can put that one over there. We can obviously, actually it might make, what's the most sensible way to write this? I mean, any of these, it's more about sort of writing this in a sensible way now than writing it in necessarily, because all of this is just a correct finite difference approximation. I'm just going to stick them all on one side. So I'm going to get U x n t I minus 1, because that's old, plus delta t squared u. Now this is the interesting one, because that's going to pick up a, it's got a minus 2 there. It's also going to pick up a minus whatever the inverse of this is. So okay, so this is equals 0. Right, so this tells us how we can go from one time level to the other, right? So let me just go and look at my numerical thing. I just want to check if I've got enough time to actually do this before I embark upon it, and I also want to check that I've written down sensible stuff. Come on. Sorry, my file isn't opening. Ah, there we go. Oh dear. I think I've blundered in my time step, in my minus ones. I think these all need to be at the old level as well. Yes, they do. That makes so much more sense. So let's just, yes, I even wrote +1 there. That's stupid. These should all be at the old time level. So these are not present time levels. They are old time levels. And here, -1, -1, -1. Oh, and that means that this this diagram's slightly out as well. This is -1, -1, -1, and we arrive at ni like so. Yeah, so we use information at these 3 points to get to one new point in both space and time. And we can now, yes, this rearranges much more sensibly. This just goes over the other side, and we get something that kind of resembles the Euler method, right? Because we really have just used something that must be equivalent to the Euler method in time. Sorry, my writing's getting sloppy because the font's the screen's too zoomed. So all of this is known. This is our unknown, new unknown. All right, so I'll just pause there. Is everyone happy with this? We're not totally lost. We've used our finite difference approximation to the second derivative in space and the first derivative in time to construct this big, long, awful looking expression. We can now go ahead and figure out how we're going to apply this in MATLAB. I don't think I've got time to do the whole coding, but instead what I'll do is I'll just go through, I'll write pseudocode for this, and then we can call it quits after I finish that. So the heart of this thing is the loop where we iterate over both time and space, right? So we know that we have to iterate over the i's and n, right? So that's what we're going to work out how to do now. Loop over I, right? We loop over time first because obviously leads the ends, right? So all of this is at t minus 1, right? So our goal is initially to do this, right? We want to evaluate this, and then we advance time. So time is going to be the outer of the two loops, right? So we want to solve for all spatial points before we advance in time. So we loop over time. Inside that loop, we're going to have another loop over space, n equals 1 to capital N minus 1, right? So we're assuming we discretize our line L on 2 to L on 2 like that. We're going to call this point 0, call that point 1, 2, miss a few, n minus 2, n minus 1, n. Right? These boundary points, I know the value there, right? And I can always, I finished my spatial loop. So end loop, apply boundary conditions, right? Because they're just things like u at x0 t whatever k, let's say we're at the kth step, that's just equal to, say, 0 for now. So we're going to have an expression like x0 equals bc1 hardwire that 0 in. We'd call it a variable. Or we could do it like that if we know that our boundary conditions are never going to change. All right, so that's what we have to do. So that solves, inside this loop, which we haven't worked out yet, that solves all our spatial points except for the boundary conditions. Then we solve for our boundary conditions. We apply our boundary conditions, and then we know our u in space at the old time. We then want to advance to the new time. So we can then end the time loop. And here is where we do things like plot output. All right, we'd plot the temperature as a function of time. We might compute errors here. Anything that we want to do with the data, we would do it in this part of the code because we need that time error data at every time step, right? Or we want to see what how this solution changes in time, right? That's the thing to easily visualize with a movie, all right? We would do that there. In here, we want to apply a finite difference formula. So this is where we do this step, really. We take all of this stuff that we've worked out and we put it in here for our unknown. So I'll just write that down. U of x n t I, right? This is our new time, right? So that's the coefficient that we worked out. There's a u, x, n minus 1, t, I minus 1. This gets a minus 2. Let's just make sure I've got that right. Yep. And then my last u. Like so. We do that in there, right? How we store this in MATLAB, for example, we might call this u old. We might call this u new, right? We want to change, we want to overwrite the definition of what's old and what's new every time we go through the loop. So at the end of the loop here, right, the end of the time stepping loop, before we go to the next step, so we do our data processing, we look at our solution, but here we'd want to replace u old equals u new. Right, so after we've looked at all our data, we discard our old data, our and we replace it with what we've had. That's our advance to the new step. So inside the time loop, up here, we don't really need to do very much. We might need to calculate an exact solution. We might need to set the initial condition, things like that. But for now, we're not doing any of that. We're just trying to solve this PDE. So there's nothing to do in there. So this would be like 4, and then another 4 immediately after it. Up here, we're going to have to do some work. We've seen that we need to define a lot of stuff. We need to define our grid. X. We've got to define delta t. We've got to give a value k. We've got to give a value for delta x. We might have to define this BC vector if that's how we wish to store our boundary conditions. We have to define L. We have to define N. Right? All of that, how long we're going to integrate for. So T max, if you like, or in this case, it would be I max, right? The number of iterations that we're prepared to do. What else would we need to do in here? We would need to define our initial condition. So this, we've started it at 0, right? We actually have an initial condition at 0. So we really should start at 1 immediately after our initial condition. So we could define u old here equals our initial condition, which was, I think it was a Gaussian. It was a Gaussian of a really strange shape initially. Let's just say it's e to the minus x squared, like that. Right, that'll do for an initial condition for now. E.g. That looks like, if you don't know, this is our x, this is our initial u, this is our UIC. It'll look like a bell shape, right? Symmetric around the origin. The boundary conditions might not quite be satisfied, right? If they're 0, you have to go to a plus or minus infinity, so L has to be big for this to be a suitable initial condition. But that, for the moment, is what we'll try. All right, and that should be enough to start building our MATLAB solution of this problem. Do we want to call it quits there, or do you want me to start doing the MATLAB solution? I think it's not, I'm not going to get it finished. There's 10-15 minutes left. What do you reckon? Do you want me to start? Or do you want to have like an early dinner?
I think we could probably go for an early dinner, Duncan. That's
alrighty. That sounds great to me. All right, we'll resume our discussion on this. Are there any questions? Firstly, are people happy? All right, so I guess the next thing that we're going to do after we finish this example is going to look at stability in a PDE context. So I think that that's and this is the type of example that's used to study stability. So have this example in your mind in future lectures. Otherwise, if there's no questions, I think we can all get going. No worries, mate.